video 73 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is coupled and time-dependent Hartree-Fock. In this section, I want to go through the derivation of perturbation theory expressions for second-order properties, similar to what we have done in chapter 3, but now not starting from the exact Schrödinger equation, but starting from the Hartree-Fock equations, which means that we will derive an approximate expression for second-order properties, expressions which are consistent with the approximations made in Hartree-Fock theory. And this approach is called the coupled Hartree-Fock method, CHF, or sometimes also the coupled perturbed Hartree-Fock method, CPHF. So we start from the Hartree-Fock equations, but now the Hartree-Fock equations in the presence of a perturbing field F. So our Fock operator is now field dependent, and then of course the eigenfunctions, the orbitals are going to be also field dependent. The orbital energies are also going to be field dependent. In addition, the orthonormality condition for the spin orbitals, which we have in Hartree-Fock theory, also applies now to the perturbed occupied spin orbitals. So here's the orthonormality condition for that. Similar to unperturbed Hartree-Fock theory, we will expand also our perturbed spin orbitals in a set, but quite contrary to normal Hartree-Fock theory, this is not going to be the set of our basis functions directly, but we actually will expand our perturbed orbitals in the set of unperturbed orbitals with some expansion coefficients U here, which will be field dependent then, because the unperturbed orbitals are not field dependent, so it's our expansion coefficients which are field dependent. And the expansion coefficients will be put in a matrix for which we use the symbol U, which of course indicates that this matrix is going to be a unitary matrix. One of the advantages of this expansion of the perturbed spin orbitals in the set of unperturbed spin orbitals is that then the unperturbed Fock matrix is going to be diagonal in the spaces, because the unperturbed spin orbitals are the eigenfunctions of the Fock matrix. So in the basis of its eigenfunction, of course, the Fock matrix is going to be diagonal. What we do now is to insert this expansion of the perturbed orbitals up here into our perturbed Hartree-Fock equations. That is done in here. So we have the perturbed Fock operator acting now on this expansion of the perturbed spin orbitals, and also here the perturbed orbital energies multiplying this perturbed spin orbitals. And the same way we will insert it in the orthonormality condition, where we of course have another term originally which includes the overlap between the unperturbed orbitals, but the unperturbed orbitals are orthonormal, and therefore we end up with this condition here. Now, like the solution of the Hartree-Fock equations in the Rotan-Hartree-Fock theory, what we do now is we pre-multiply our perturbed Hartree-Fock equations with another one of these basis functions, which are here our unperturbed orbitals, and then we integrate over full space, which then turns this differential equation in a matrix equation. So here we get now an element of the Fock matrix in the basis of the unperturbed orbitals, where we have Q here because we had psi Q here, and we pre-multiplied with psi R, so therefore we have the index R here. And similar on the right-hand side, we can then get the overlap between psi R and psi Q, both unperturbed spin orbitals, and they are of course orthonormal, so therefore we get a Kronecker delta here. So this is now our perturbed Hartree-Fock equations in a matrix form. Let's now have a closer look at this perturbed Fock matrix. So the perturbed Fock matrix is or the elements of the perturbed Fock matrix are these kind of integrals where we have two unperturbed spin orbitals and the perturbed Fock operator. Now the perturbed Fock operator has several contributions. It has, of course, the normal core Hamiltonian, H zeroth order, which is the kinetic energy term, and the electron nuclear attraction term. Then it will have our first order and second order perturbation operators, as we have derived them in chapter 2. And then, of course, the Fock operator includes the averaged electron repulsion term, which means that to the Fock matrix we will get terms which are sum over all the occupied orbitals, and then Coulomb exchange integrals where we have the psi p and psi q here for electron 1, and for electron 2 we should have all the occupied orbitals psi j. But those are perturbed orbitals now because we have this is the perturbed Fock matrix. And these perturbed orbitals psi j, we expand now again in the unperturbed set of orbitals, and that's where this sum over all orbitals s and t comes from, and therefore we have here s and t, and also here s and t, and we get this unitary transformation matrix again. This means that the perturbed Fock matrix also depends on these expansion coefficients u. Later on, it will be also useful to remember that we express the first and second order perturbation operators as a product of a component of the external field, here for the first order term, one component external field, and an operator which solely depends on electronic coordinates or momentum or electronic spin. And the second order Hamiltonian is then the product of, again, such an operator with two components of the field. Now comes perturbation theory, which means that the Fock matrix, the field-dependent Fock matrix, the field-dependent orbital order energies, and these field-dependent expansion coefficients will all now be expanded in the perturbation series. And as the first term, of course, we get the unperturbed Fock matrix and the unperturbed orbital energies and this unperturbed expansion coefficient, and then we will get first order terms and second order terms and so far. For the derivation right here, I only need the first order terms. And we will write the first order terms directly as a product of the corresponding component of the field here and a first order correction to the Fock matrix, to the orbital energies, and to this expansion coefficients collected in these unitary matrix U. Now, since we are in the basis of the unperturbed orbitals, the zeroth order contribution to this expansion matrix is diagonal. It's just Kronecker delta, because in the zeroth order I just should get the orbital I back. And also the Fock matrix, which is now the Fock matrix in the basis of the unperturbed orbitals. So the zeroth order Fock matrix is also diagonal, and on the diagonal we have the corresponding orbital energies. In addition to the expansion of the Fock matrix, the orbital energies, and this unitary transformation matrix, we also can directly look at the orbitals. Here the occupied orbitals, perturbed occupied orbitals, which is expanded in, of course, the corresponding unperturbed orbital, and then corrections. And the correction here is, of course, the sum over all the unperturbed orbitals multiplied with this first order unitary matrix times the component field for the first order correction and the second correction correspondingly. We can also look at the density matrices, the Hartree-Fock or STF density matrix here expressed in the atomic orbital basis or in the basis of the basis functions, which of course is also going to be perturbed. So we get as the first term the unperturbed one, and then we can get a first order correction. And comparing the expression for the expansion of the orbitals and the density matrix, we can see that this first order correction then actually looks like this. It is sum over all the occupied orbitals, and instead of having just product of the molecular orbital coefficients here, as we would have it for the unperturbed density matrix in the atomic orbital basis, we now have one first order orbital molecular orbital coefficient and one zeroth order molecular orbital coefficient and the other way around combination. And we can also show that this is actually the same as just the sum of two elements of this unitary transformation matrix to first order, which means that the first order correction to the density matrix can be directly calculated as soon as one knows the first order correction to this U matrix and has transformed it to the atomic orbital basis. Now we can insert all these expansions in our perturbed Hartree-Fock equations and then, like normally in perturbation theory, separate orders. And the first order perturbed Hartree-Fock equations then take this form here. And correspondingly, the orthonormality condition for the spin orbitals to first order takes this form. Now we know what the zeroth order terms are here. At least we know that the zeroth order Fock matrix in this spaces is diagonal, has the orbital energies as the diagonal elements. We know that this zeroth order unitary transformation matrix is just a Kronecker delta. So we can insert that here and there and also here, which then reduces this equation up here to that equation. So here we have a difference of orbital energies, unperturbed orbital energies, times an element of this first order correction to the transformation matrix, to the matrix of the expansion coefficients. And that is equal to one first order correction to the orbital energies minus the first order correction to the Fock matrix. And we can see that the orthonormality condition just reduces to this expression that the sum of these first order corrections to the matrix of expansion coefficients has to be 0. Now, if you consider the case that the R is not equal to I, where I are the occupied Hartree-Fock equations, here, then therefore only look at the equations where R is a virtual orbital A, and now insert also the first order expression for the Fock matrix. And then we can try to collect all the terms which include the U's on one side and the orbitals. Then we can reformulate the first order correction to the perturbed Hartree-Fock equation in this form, which means that we could directly calculate an element of this first order U matrix if we know the first order correction to the Fock matrix and divide by the zeroth order orbital energy. However, one should not forget that, of course, the first order correction to the Fock matrix also depends on the U matrix or the first order correction to the U matrix, which means one has to solve this equation here iteratively. And again, I have written here up the first order correction to the Fock matrix, where we here have just an integral over this first order property operator, and then here we have our Coulomb exchange integrals multiplied with the first order corrections to the U matrix. To our what I have now, in principle, the perturbed occupied orbitals could or should be expanded in all unperturbed spin orbitals. However, we might have already discussed when we discussed our Fock theory that a mixing of occupied orbitals does not change the Hartree-Fock wave function. Therefore, we only actually need to expand the unperturbed occupied orbitals in the virtual orbitals. And therefore, we only need to determine the elements of that unitary matrix where we have a virtual and an occupied index. Let's also go back on in this equation here. So now I have back to the original first order Hartree-Fock equations. This is first order, and I have collected all the terms which involve the first order correction to this transformation matrix on one side, and I only look at the ones where I have virtual orbitals. and that is these equations. We can now recognize the equation in the parentheses here as being the A and B matrices from the random phase approximation as we have discussed it in chapter 10, where this here is the A matrix, and it's the A matrix actually up to first order because this is the zeroth order contribution to the A matrix, and these are two integrals are first order corrections to the A matrix, whereas these two here is the first order B matrix. Write the first order Hartree-Fock equations also in this form where we have sort of replaced the integrals by the corresponding A and B matrices. Now, depending on what kind of operator we have in here, whether it's a real operator or imaginary operator, has a consequence for whether the complex conjugate of the U matrix is then going to be the same as the U matrix or whether it's going to be minus the U matrix. So for real one, we have this one, and from imaginary, we have this one, and therefore we can combine them together, both cases in this expression, where the upper sign is for real perturbations and the lower sign is for imaginary operators here. So the operators there. Now, these equations here, which are our first order Hartree-Fock equations, you can hopefully recognize as being linear equations, inhomogeneous linear equations, because the right-hand side is not zero. So we have a set of inhomogeneous linear equations which can be solved for this first order correction to the U matrix, which is the unknown in this equation. Having obtained this first order correction to the U matrix, we can now look at the first order correction to the spin orbitals, but we can also look at the energy, which means that's what we want to do here. So here's the Hartree-Fock energy, but the perturbed Hartree-Fock energy, so in the presence of a perturbing field, written up in the way with the orbital energies and the correction which removes the double counting of the electron-electron interaction. And where we, of course, since we are in the presence of an external field, we have the orbital energies to be field dependent. And we have replaced here in the Coulomb exchange integrals already the otherwise field dependent spin orbitals by the expansions in the unperturbed spin orbitals with the transformation matrix here, which are now field dependent. And then one can expand this field-dependent Hartree-Fock energy, of course, in the unperturbed Hartree-Fock energy, a first-order correction and a second-order correction. And if one does that and then inserts this after some derivations, one can arrive at the second-order correction to the Hartree-Fock energy, which takes this form here, where we have a contribution which is just integrals with the occupied unperturbed spin orbitals of these second-order perturbation operator. And then we have a second term where we have integrals with occupied and virtual orbitals and the first-order perturbation operators, but those multiplied with our first-order correction to the expansion matrix. If one then compares this expression for the second-order correction to now the Hartree-Fock energy with the general expression for the second-order correction to the energy, to the exact energy as we have derived it in chapter 3, then we can see a clear similarity, because this term here, where we have the second-order property operator, corresponds very much to the expectation value of the second-order correction to the Hamiltonian. And these terms here, or this term, where we have a sum over occupied and virtual orbitals, and we have property integrals over the first-order property operators, and we have these first-order corrections to the expansion matrix, corresponds to the sum over states expression, where we would have had transition moments with the first order correction to the Hamiltonian. In order to get now second order properties, we have of course taken the derivative of this expression with respect to two components of the fields, which is trivial because I had written up the expression already with the fields explicit written out, and we get this then as the coupled Hartree-Fock or coupled perturbed Hartree-Fock expression for a second order molecular property like a static polarizability or magnetizability or the paramagnetic contribution to a shielding constant. And in order to evaluate this, one needs then property integrals here over the occupied orbitals and here occupied and virtual orbitals, and one has to solve this first order coupled Hartree-Fock equation in order to get this first order correction to the unitary expansion matrix. A few slides back, we had introduced in the expression for the first order correction to the Fock matrix the A and B matrices of the random phase approximation. In the next two slides, I want to make the relation between the random phase approximation and this coupled Hartree-Fock more clear. In order to do that, I take now the complex conjugate of this first order coupled perturbed Hartree-Fock equation, which we had before, and combine the original coupled Hartree-Fock equation with the complex conjugate to a big matrix, which then can be written in this way, where here we have the A and B matrices, and we have our U matrices, and here the original U matrix, and here the complex conjugate, and this one has a minus sign. And on the right-hand side, I have used the symbol O here for the vector of these property integrals. And writing in this way, it clearly becomes clear that the U matrices are the solution to this inhomogeneous set of linear equations. We can also write it explicitly out that these U matrices here are obtained by calculating the inverse of the what looks like very much like the RPA matrix times the vectors of the property integrals. Comparing that with the expression for RPA in chapter 10, we can see that this U matrix here is actually the same as the excitation part of the RPA solution vector for a static property, so for frequency 0, and minus the complex conjugate is just the de-excitation part, which means the random phase approximation for 0 frequency is exactly the same as coupled Hartree-Fock or coupled perturbed Hartree-Fock. Now let's look at the time-dependent case, which means let's look at time-dependent Hartree-Fock theory, TDHF. So this is essentially a generalization of the derivation which we had done just before to the case of a time-dependent field. And here we also will look at the monochromatic linear polarized radiation. And we'll again use the dipole approximation or the long wavelength approximation. Now, like in the coupled Hartree-Fock method, in the time-dependent Hartree-Fock method, we also expand the spin orbitals, which are now perturbation and time-dependent, in the corresponding perturbation and time-independent spin orbital, and then a series of corrections. And these series of corrections are again, like we just had, expanded again in the complete set of the unperturbed orbitals, where we have again these unitary transformation matrices. But now they are also frequency dependent, and we have two terms. Again, we have one with the positive frequency and one with the negative frequency, because we expand the frequency dependence of the field, which normally would be cosine omega t, again using Euler's relation in the exponential with positive frequency and with a negative frequency. Now, we have now, like for normal coupled Hartree-Fock the static case, we have to then derive equations from which we can evaluate or determine these expansion coefficients collected in these unitary matrices. And Since we are now in the time-dependent case, we need sort of a time-dependent version of the Hartree-Fock equation. And they can be derived, and they look like this. Um, they differ from the normal Hartree-Fock equations that there's an additional term to the Fock operator, which is just the time derivative. Now, starting from this time-dependent version of the Hartree-Fock equations, we can do precisely the same procedure as we have done for the time-independent case. There are a slight complication because we have the time derivative here, but at the end, we arrive at these equations here, which are the time-dependent Hartree-Fock equations, which are the equations, a set of, again, inhomogeneous linear equations from which we can determine the elements of these U matrices as the solution. And if one compares these equations with what we had for the random phase approximation in chapter 10, we can see again exactly that the U matrices are actually just our RPA solution vectors, the excitation part and correspondingly the de-excitation part. Which obviously means that time-dependent Hartree-Fock theory and the random phase approximation are the same theory. The derivation just starts from different points. So these two methods are essentially the same. Now for static properties, the Coupled-Hartree-Fock approach was originally favored because it could easily be formulated in the basis of atomic orbitals, which then made it easier to carry out this calculation because it did not require transformation to the molecular orbital basis. Whereas the random phase approximation originally was normally formulated in terms of molecular orbitals. On the other hand, Coupled-Hartree-Fock is a static approach, so there's no frequency dependence, which means that one could not calculate excitation energies with the Coupled-Hartree-Fock approach, and one could not calculate frequency-dependent properties, as one can do with the random phase approximation or time-dependent Hartree-Fock. Now, that distinction nowadays is anyway gone because one can also now there are also now formulations of the random phase approximation and the generalization to a higher order, like the second order polarization propagator approximation as introduced in chapter 10 to atomic orbital basis. So also random phase approximation and super calculations can nowadays be carried out in the atomic orbital basis.